We are Team 7 for Senior Design 1. Our team name is J.O.M.K.L Appliance. Our team project is R.O.S.I.E, which stands for Ready-Made Operating Stove Integrated Environment. My name is Juan Jimenez. I'm electrical engineering. I'm concentrating in power.
My name is R.O.S.I.E. I'm a computer engineering major, and I'm concentrating on computer design and programming.
My name is Michael Ferrer. I'm an electrical engineering student. I am concentrating in communications and biomedical engineering.
My name is Kenny Martinson. I'm studying computer and electrical engineering, and I'm concentrated in communications.
My name is Lucas Pastorini. I'm an electrical engineering major, concentrating in communications, controls, and power.
I will now be giving you a brief introduction to the R.O.S.I.E system. This is what we plan our stove to look like. This is the GUI where the user will interact with the stove. These are the 4 burners. Each burner will be assigned an infrared thermometer and a probe thermometer. These sensors will relay the information of whatever is being cooked on each burner and send it back to the system where comparisons will be made. The GUI, we plan on incorporating a touchscreen for easy access while you're cooking. Each burner will be controlled by a digital control. That way, the user can control the controls of the burner independently of the system or with the GUI, but not both at the same time. In this diagram, you see the user. He has 2 options. He can either use the GUI and the logic, which control the stove. The stove gets its information from the sensors, which is relayed back to the logic, where the comparisons are made and final controls are sent to the stove. Or the user has direct access to the stove, bypassing the GUI and not using the sensors. Here, the user will be able to control the stove like a regular household stove. This chart shows the flow of how information will go through our project. The user selects food from a menu stored in the GUI using this touchscreen. The system will load the FDA's recommended food cooking temperatures for whatever item the user is intending on cooking on the burner. The sensors, depending on which burner, will gather the food from the food as it's being cooked. It will be sent into the system, into the logic. It will compare, is the food actual temperature equal to the FDA's recommended minimum cooking temperatures for each individual food? If yes, the food is complete. The stove will turn off and notify the user. If no, this will loop around and continue to gather information from the sensors, continuing to make the comparison until it finishes yes and completes the loop. Thank you.
Our stove consists of analog control knobs. We are converting those to digital controls, so in order for the microprocessor to control those digital values. As you can see here, the electrical outlet provides 240 volts for the stove. We are attaching that to a thyristor, which is a silicon controlled rectifier. That is going into the anode. According to the gate voltage that's applied to the thyristor, we are going to get, for each step, we are going to get a certain amount of voltage of alternating current to go to each burner. On logic step number 8, at 13.28 milliamps, with 100 ohm resistance in the gate, should be 1.328 volts. In our digital to analog converter, we will supply 1.328 volts to the gate and will allow 213 volts alternating current to pass through to each burner to supply this amount of voltage for the temperature. What was that? What we got here is 2 circuits. Our first circuit is our 7-segment display, currently outputting logic step number 8. That is our digital input. That digital input is going to go to the R2R ladder circuit, which is a digital to analog converter. From logic step number 8, according to our calculations, that the output of that R2R ladder circuit is going to give us 1.36 volts. As you can see here in the diagram, is logic step number 8, 1000. According to our multimeter, it is 1.36 at an input voltage for the logic step at 5 volts.